Welcome, everyone, to Westcliff University's Distinguished Innovator Speaker Series. And our fifth speaker in this series, Dr. Jacopo Annese, who's going to talk about really the most famous neuroscience patient that ever existed. I'm Dr. Barry Sandrew, Director of Entrepreneurship at Westcliff University, and I'll be your moderator this evening. And I'm really very happy you're all able to join us. We'll get to Dr. Annese in just a moment. But first, I want to briefly introduce Westcliff University to those in the webinar audience who might not be familiar with the institution. Pictured here is our campus in Irvine, California. Westcliff is an accredited private institution with approximately 3,500 students enrolled both online and face-to-face on campus. There are 4 colleges. The College of Business offers bachelor's, master's, and doctoral degrees in business administration, as well as certificate programs. The College of Education offers a BA, a master's in teaching English as a second language, and the Real Intensive English program, as well as certificate programs. The College of Law offers the Juris Doctoral degree and certificate programs, and the College of Technology and Engineering offers a BS and MS degree in IT, an MS degree in computer science, and an MS degree in engineering management. For more information on the university, I invite you to visit our website at westcliff.edu, as well as Westcliff University on Twitter, Facebook, and LinkedIn. And now for just a little bit of housekeeping. You've all joined this webinar in listen mode only, which of course means that you're all muted. But I welcome you to use the questions pane on the bottom menu to participate with Q&A and during the entire presentation. And I'll be monitoring that, and I'll be presenting questions to Dr. Annese during my interview with him, as well as during my presentation and his presentation. What I wanted to do initially, well, first of all, I wanted to welcome Dr. Jacopo Annese. Welcome, Dr. Annese. Really appreciate you being here.
Thank you, Barry. Thanks. Thank you for inviting me.
Yes, and what I'd like to do, if it's okay with you, I'd like to give a little bit of background because this is a unique subject that you and I have a special bond, both professionally and emotionally, about this particular subject, which is kind of unusual. And I wanted to just go through a little bit of background about the state of neuroscience, the state of our knowledge of the brain in the 50s, 60s, and 70s, even the 70s. Back then, well, even in the 1800s, we didn't know a lot about the brain. I mean, what we did know about the brain, and please interject wherever you wish, what we did know about the brain came from patients that presented with brain damage. One of the most famous is Phineas Gage. He's right there on the left. And he was worked on a railroad, and he basically was tamping down gunpowder, and the rod that he was using went in through his skull and into his frontal lobes. He survived, as you can see. He's sitting there with the tamping rod, so he survived. But the interesting thing is that his personality changed 180 degrees. He went from a very calm and gentle giant to a very flamboyant person with fits of rage. But that type of investigation actually led to what we knew about the brain up until the 70s. It was basically based on brain damaged individuals, people who had gotten in accidents. There's 2 examples right there on the right. There's Broca's area in blue. Dr. Broca studied some patients who had damage in that part of the brain on the left side, and he discovered that they couldn't talk. They couldn't vocalize anything. They basically had guttural sounds. And then Wernicke studied patients that had damage in the orange part, and that really was involved with the interpretation of speech. So these people could talk, but they couldn't really understand speech. So that was really how we knew how the various parts of the brain worked, at least what parts of the brain were involved in what sort of functions. And over time, we got to know more and more about how the brain, or what parts of the brain were involved in what. We knew what parts were involved in hearing, in vision. We knew what parts were motor and all of that. So it was invaluable to use patients because that was really all we had. There was one other way of doing it, of course, and that was using animal models. Neuroscience, we used to use monkeys, and we'd train them on various tasks, memory tasks and other types of tasks. And then we would remove part of the brain and then retest them and see if it had any effect. And that's really the most valuable way of studying, especially the subcortical parts, the inner parts of the brain, because they're normal. They were essentially normal uh, organisms, and we could test them, and there were no complicating issues with their mentality. So that's basically the way things were. Um, but that didn't stop a lot of neurosurgeons back in the 50s, 60s, and 70s to use procedures to try to influence the brain. This is one particular individual. His name is William Beecher Scoville. He was one of the most famous neurosurgeons around that period of time, 50s and 60s. He turned out to be one of the most prolific lobotomists back then because, while we didn't understand much about the brain, there were a lot of patients, mental patients, in both state institutions and in private institutions with debilitating mental illness. And there was no way to really treat them. The medicines they were Thorazine, Stelazine, that made them basically into zombies. So one way to treat them is to give them a lobotomy, cut the fibers in the frontal lobes, and they became passive and controllable. The problem, of course, is that they lost all of their personality. They lost all of their what they were was gone. So it really didn't help them, but it just managed them. And he wasn't the most prolific. There was another one that was even more of a proponent for lobotomies. But that was basically where things were in that period of time. Now, the practice of medicine, obviously, today is significantly different than it was back in the 50s, 60s, and 70s. It's completely different. It's like light years different. But back then, the the line between medical practice and experimentation was very, very blurry. And these surgeons were very cavalier about how they treated these patients and what they did with them. And to a large extent, they didn't know whether what they were going to do had any effect whatsoever. And in many cases, they even referred to some of their patients in mental institutions as material, believe it or not. They were dehumanized, and it was like the dark ages of medicine in terms of neurosurgery anyway. But this gentleman here, he was chief of staff at Hartford Hospital. He was um, uh, he was one of the most famous neurosurgeons in the world. I believe, he was head of the American Neurosurgical Society, and um, so he was very well known. You
And
know,
very, I
yeah,
think those tools are made by him. He was very proud of the fact that he would make his own tools.
you're absolutely right. And the other one, I can't remember his name right now. Freeman. Freeman. Yeah,
Freeman,
he
yeah.
actually modified a an ice pick to do lobotomy. So yeah, they were very proud about these new tools that they could use to actually create lobotomies. But they thought they were doing good work. In fact, Scoville had a personal issue, personal goal. His wife was psychotic, and he was searching for a solution for her. So, I mean, the intentions were good, but the practice was pretty medieval, looking backward.
Looking back,
Back,
yeah, I think
yeah,
I think that they thought themselves as explorers,
Yes.
And they were given a lot of freedom, a lot of, free reign to, because there wasn't much oversight institutionally, and
Hmm.
sometimes even the patients didn't have really a family behind them or with them. So it was, but in the case of the patient HM, as maybe we will mention later,
Yeah.
um, Scoville was very frank about this operation being this particular lobotomy, which was a real lobotomy, was a real lobectomy, in fact,
Lobectomy.
of being experimental. So it was very frank about it, and the family gave permission because there were some indications that removal of the medial temporal lobe would help with the epileptic seizures that Henry was suffering
Yeah.
from. I have a couple
Yeah.
of slides just at the beginning to tell the story quickly.
Okay. Yeah, I was just
Uh,
getting to that. I mean, so there were no
there you
normal
go.
people, but there were no normal people that they could experiment on. I mean, why would somebody, allow a neurosurgeon to actually take out part of my brain if I have no problems? Well, HM, when he was 7, fell off his bike and hit his head, and he developed seizures, and they became debilitating. And in the late 40s, he went to Scoville, and Scoville gave him anti-seizure medicine that didn't really help. And then in 53, like you said, Jacopo, he basically said to HM, Henry, I want to try this experimental procedure to try to relieve you of your seizures. He was perfectly normal in every other way. So for the very first time, a normal individual went through a lobectomy, basically taking out a portion of the brain on both sides, and it was basically the hippocampus, the entorhinal cortex, septum, and amygdala, which is part of the limbic system. And he didn't really know what was going to happen. He just thought that this probably would cure the seizures.
Well, he was also part of a group of patients. I think he joined the group of patients that were undergoing this procedure, but all the other ones were psychotic to begin with. So they did have something wrong, to put it like you said. And I think, like, HM was the only one. In fact, Henry, we call him Henry until he had the surgery, and then he became patient HM. Uh, Henry was, like you said, the only one who was normal, besides the fact that he had these seizures that might have been caused by the bicycle accident, might not have been caused by that. And but nevertheless, fact remains that they agreed. And at that time, they didn't know. I mean, at the time, the medial temporal lobe is still removed in epilepsy, but only on one side of the brain.
Mhm.
I think HM taught a very valuable lesson, and that surgery was never repeated.
And Jacopo, why don't you continue and tell what the result was of that particular surgery?
Uh, Let me know when yeah, I have a couple of drawings. I was gonna accompany the story. They're like
Okay.
some illustrations made by a very dear friend of mine who's also a neuroscientist. Um, so this is Henry. Strange to believe, this is a photo from high school, from the high school yearbook. They were very proper then. And so HM was, when he underwent surgery, he was 27. Let's just tell a little bit of a story. So HM was 27, and this was 1953 when
Mhm.
he underwent this fateful surgery. What happened, as Barry said earlier, uh, they knew that the hippocampus in particular, but all of the brain structures that were sitting along the medial temporal lobe, the temporal lobes are on the side of the brain. The medial temporal lobe is essentially the inner side of these two lobes. Uh, the brain is divided into two hemispheres, as you guys know. And at the time, there were there was some hint that these areas were, and this was validated later, and to this day we know that there are pathologic changes in the hippocampus in the case of epilepsy. And so it made sense at the time to try to remove these areas because nobody knew what they were really used for. And it was done bilaterally. So this was a bilateral lobectomy. Uh, what happened though, Henry, the surgery was uneventful in the sense that it was performed and it didn't seem, there were not any complications. The complications started a bit later. HM also was not unconscious, but when he eventually recovered from the surgery, the staff of the hospital started noticing some strange behavior. He did not recognize, for example, the nurses. He did not recognize the doctors that he had spoken to only a few days earlier, and it started appearing odd, more odd and odder as time passed. Essentially, it became clear because, like Barry said, otherwise he was completely normal intellectually. He was a healthy young man with intact cognition. And so the amazing thing that happened after that surgery is that everything else remained intact in terms of the way he thought, his IQ, relatively speaking, of course. But something was missing, and it was very, very specific. And it was the ability to actually remember facts, remember people he saw, which would be called, declarative memory. So when HM was repeatedly interviewed, even later, many, many decades later, and you would ask him, what did you have for lunch? What did you do this morning? He would not be able to say. He could have taken notes, of course, and then answered. But in terms of keeping in mind and remembering what he had just done, this type of memory was completely gone. Maybe less famous. So again, why was he famous? Because this was the first time that the field in neurology, the neurosurgery, it was the first time that they realized that these areas in the middle temporal lobe had something to do with were necessary, at the very least, maybe not sufficient, but they were necessary to create memories. But there was another thing that HM, maybe not as famous as the fact that HM was really important in the field, is because he also demonstrated that there was not only one kind of memory in the brain. So the memory was not just one function. In fact, this was a later experiment that this young researcher, Dr. Brenda Milner, performed. And it was an experiment, essentially, it seems very trivial. The patient is asked to draw with a pencil within the lines of this star. Now, this is trivial, unless you have to do it only using a mirror image as a guide. So in a mirror image, everything is reversed. So now your visual system is giving the wrong cues to your motor system. And it's something that can be quickly learned as an adaptation. So in fact, people with a normal memory and with no lesions whatsoever, they are able to learn in a few trials. And the expectation was that Henry, a.k.a. patient HM, would not be able to do this because, if he lost his memory, how can he learn something new? As a matter of fact, he did perform pretty much just as well as normal subjects, as normal individuals, within the range at least. And that demonstrated that, we don't have just one kind of memory, but there is the declarative memory that we mentioned before, and there is this other kind of memory, which is procedural. Please, go ahead, Barry.
No, I was going to say that one thing that he didn't remember ever doing it before. He learned over time, but he never
remembered. This is very important. Yes,
yeah.
Thank you. This is a very important fact. So, in fact, it's almost, I would think, sweet of him. I mean, he learned better, but he could really, like he said, he could not remember having taken this test. So it was really interesting. And this, I think this evidence combined made him into what he became, really a professional research subject. And he must have been, I think a few hundred researchers worked with him in person at one time or another. But if you do a PubMed search, if you do a search for scientific papers on HM, I think you'll find thousands of publications where he's mentioned. Also because, as Dr. Squire put it, in a sort of an article after HM died, he was really the measure for every other amnesic patient that came after him. He was the yardstick that was used to measure the severity of the memory impairment of patients after that happened after him for other reasons. As I mentioned, the surgery was never replicated. But herpes simplex encephalitis can create very large lesion in the middle temporal lobe and cause very severe amnesia. And this is what happened to later patients. But HM was always sort of the baseline. Now, how do these patients compare to HM? They always refer back to HM. Also in terms of the severity of the pathology and the actual size of the lesion in the brain.
Yeah, I might say that you've taken a course in psychology. Every psychology, introductory psychology book mentions HM and
Yeah,
memory.
absolutely. Yeah. And they will always do. I mean, after I was involved, I became involved with HM's brain. I received, as you know, I regularly receive a lot of requests from editors of textbooks for images, and I try to, you know, as we will see a little later in the presentation, the story is not that this simple. It turned out after we examined the brain, we realized that, you know, this was not a clear-cut example of lobectomy, and but nevertheless, textbooks are very interested in this story. And I try sometimes to correct them and say, look, there's new data, new evidence. No, but it's fine. You know, we like the simple story. Hopefully soon this text will be updated as well. So HM, arguably one of the most important medical patients in neurology. And Barry asked me to make this a bit of a more of a personal type of presentation. How did I get involved? So at the time, I knew Dr. Sue Corkin, who was the researcher who studied HM for several decades. And in fact, Sue Corkin took over Dr. Brenda Milner and took on the responsibility of working with HM. And she and I had met several times at scientific meetings. So I was aware of HM. And at the time, I was setting up my new lab at UCSD here in San Diego. And my goal really, what really excited me about neuroscience was to understand not so much how the brain worked. I know this sounds like a heresy, but to me, what was really interesting, maybe because of my more humanistic background from Italy, was really to try to connect the person, to try to connect the brain to the actual person who used to use it. So how does the brain, you know, what is the relationship between the brain and our talents, our personality, like Barry mentioned, and could we see also in the brain traces of the type of person that we are in terms of our abilities, in terms of our emotions. So this was what really interested me. And so purely human neuroscience. And eventually we set up a brain bank to support this project because, you know, you gotta, some people ask me, okay, but why is not MRI enough? Why do you need to have donated brains to try to study this link between anatomy and behavior? The problem with MRI, even though it is really the tool that has enabled amazing progress in neuroscience, at least understanding the human brain. So we don't have to wait for patients to be hurt or to be operated on. Now we can peer, since the 80s, since the late 80s, we can peer into somebody's brain when they're alive with this non-invasive technique called magnetic resonance imaging. Now here we're looking at an MRI image, and essentially it's a slice of the brain from above. So imagine this is from the top of the head, and now this person was in the scanner, and so the MRI scanner reconstructs this image to show us. This person in particular has a few white matter hypertensities. You know, he has a little bit of white matter diffuse pathology, probably due to age and hypertension. But nevertheless, you know, as a diagnostic tool, MRI is fantastic. Even for research, if you pull data from many individuals, and this is being done in the context of very large-scale studies like the Connectome project, for example. But when you look at the single subject, you zoom in an MRI image, and in spite of the very high cost of this technology, a scanner, a new scanner can cost $3 million. This is really a very bad digital camera. I mean, when you resolve eventually, when you try to zoom in, you cannot see detail. Now, a lot of people will correct me because there are now scanners that are much more powerful, 7 Tesla, 11 Tesla, and the strength of the magnet is much higher. They really are acquiring beautiful images that rival anatomy, with real tissue. But when it comes to clinical MRI or the most accessible MRI, this is really not feasible. And I wanted to understand, how does the fine structure of the brain enable our behavior and our own personal way of being? So imagine this is the scientific context and the actual laboratory, a brick and mortar lab that I was building at UCSD. So this is in fact an MRI image of HM's brain. So I wanted to go beyond this information. So in 2007, this is a year before HM actually died, I wrote a grant for the National Science Foundation, which was more like a white paper. It was more like, what would I do if I had the responsibility of doing a follow-up postmortem examination of the brain of HM? And the idea was, we want to go beyond MRI, and we really want to understand the topography of the lesion that was created 50 years before my time. And to do that, we're going to slice the brain from frontal pole to the occipital pole in very thin section and reconstruct the brain in 3D, so we can study the lesion in every angle and measure it. The other thing we wanted to do was to create some kind of open source brain, so that I wanted, because this brain was so important, the idea was, well, how do we allow people, colleagues, researchers, to study HM's brain the same way that we do in our own lab? They cannot all travel to visit and spend time here. So how do we allow it? So the idea was, let's digitize the entire brain, and then we'll make this available as data for the scientific community to study, so that eventually, people are going to have time and patience, or passion, or both. They're going to be able to go anywhere in the brain and compare the actual data with information that can be found on these thousands of publications that have been written, and maybe even just the most important ones. So this is how the grant amazingly got funded. It got funded, and it got funded before HM even died. So then we had this grant, we were keeping it warm, and I visited HM in Connecticut, and he was still alive, but he would die after a year after my visit. So I saw him very, very late in life, and we met. He was already, unfortunately, there was already dementia had set in, and so he wasn't able really to have a conversation. But it was just incredibly exciting to be there in person and to meet him. And it was also a bit awkward because I knew that I would have then have his brain. And now with the people that participate in my project, we talk about it. I meet them, and they know that they're going to leave me their brain when they die. But with HM, there was no way of really telling him that this was going to happen. So I felt a little bit, of course, a little bit awkward in his presence. And there you go. So eventually, HM died in December 2008. And everything was ready. I had all the flight schedules because the plan was I would fly to Boston at the Massachusetts General Hospital to assist with the autopsy. So I needed to be notified as soon as HM died, and that's how it happened. So when that afternoon I got a call from Dr. Corkin that HM had died, I quickly looked at the schedules, and I literally jumped on the plane. I arrived the next morning, quick coffee, 5, 6 in the morning in Starbucks, and then we performed the autopsy in the basement of Mass General. This image is very interesting. I blurred it a little bit because maybe I should have put a slide prior saying viewer discretion of advice, like on TV, and I didn't. But nevertheless, this is actually the real autopsy of Mr. Molaison or Molaison. There's Dr. Matt Frosch from MGH, the pathologist at MGH, me, and you can see here in the background, as apprehensive as a father may be when waiting for the baby to be delivered, is Dr. Corkin. And it is a little bit, if you ever extracted the brain from a patient at autopsy, it is a bit like delivering a baby without the crying, but it's a very delicate operation, especially if you don't want to damage the brain, because the brain is very, very soft when it's not fixed in formalin. We're used to seeing very rubbery fixed, formalin fixed brains, but when it is actually at autopsy, the brain is extremely delicate. So this to me was the first step, and I was already extremely protective of this specimen because there was so much work to be done after in this long pipeline of methodologies that we had planned for him, that creating damage at autopsy would have been unforgivable. So every step was really, and you can also see here the MRIs that the colleagues at MGH had taken overnight of the cadaver that actually helped us also understand, where there would be more the sinus space, where we could work, and so we would not make a big scar on the brain surface. Then, curiously, I flew back to San Diego, and I took the brain back with me to UCSD. And I remember we flew on JetBlue. These are the actual tickets. And so that's me, and this is extra. And actually, this is Henry. And Henry was sitting next to me in a container, in kind of a cooler. And we flew back to San Diego. And that's when I like to say when the brain hit the fan, because in San Diego, which is not a very nice image to have, so we'll move on. But in San Diego, there was a lot of excitement about at UCSD about receiving these very precious specimens for study. And so the newspaper had an article about it, and UCSD unleashed their marketing power to make this a very, very visible project. So no pressure there. Now, I had a very different, I think, view of marketing. I wanted to do direct marketing, meaning we welcome all these people in the lab, and I think it taught me a lot in terms of how you work with media and news organizations. And producers can be very bossy. They come to your lab and they take over. But I think it was very important, and I tried to also control the story so it would be reported accurately. But the kind of marketing I wanted to do was more direct. I wanted to really involve the public in what we were doing, partly because it was a big responsibility. So rather than doing this work behind closed doors, I thought it was better to just be completely transparent. And if some errors would have been made, it would have been very, at least very honest. And we were all very sure about our protocols. So, but nevertheless, we opted for being extremely open about this. In fact, we'll see, we broadcasted our procedure. And the other thing was, I wanted to make sure that this was accessible not just to scientists, but also to non-experts. So this had to be, in my view, this had to be a project that was accessible by the layperson. So something that would have attracted the interest of somebody without a degree, somebody without prior interest in neuroscience or the brain whatsoever. And of course, Henry H.M. and his brain, they carried this for me. I didn't have to do a lot of work. I mean, this was a very famous brain. So this was my beginning of my science education and science outreach activities. So it was facilitated by him. But here is, in terms of a bit of science. So in terms of science, this is what we did. The brain was fixed for several weeks in formaldehyde. You can see here we change it. And the brains sit like all the other brains in our refrigerators. As an anecdote, I should mention that we had actually a decoy. We had a bucket that was labeled HM that contained not HM's brain, but somebody else's brain. And then we had a non-descriptive container with HM because, again, things were there was so much pressure about this project that I thought, you never know, somebody might play a prank, break into the lab and steal HM's brain, whatever. We were thinking of all kinds of contingencies. So we had a decoy and it wasn't necessary. So it turned out to be an abundance of caution. And this is HM's brain after it was actually all the blood vessels were removed manually. Now, I don't know how well you can see my mouse. It might be too small, but we're looking at the brain from the bottom. And you can see the lesion would be right here. So now actually, this is a very good view of the medial temporal lobes. These are the frontal lobes on the right of your screen. And these are the occipital lobes and the cerebellum in the back on the left. And this is the optic chiasm. These nerves would typically, in a person, would go to the eyes that sits right here. Mammillary bodies that were also part of the limbic system. So they turned out to be a bit atrophied, a bit smaller. And this was the first really good view that we had of the lesion. You can see this dark spot here is actually oxidation from one of the surgical clips that Scoville left back in 1953. So this was really like going back to the...
You left a clip?
Yeah, well, the clips were there, yes. And so they were removed at autopsy, but the oxidation was left. So what you see here, he essentially left the clip so that with X-ray, he could see post-op what he had done. And we removed them. We had to remove them also because we had to slice the brain. I circled, in fact, not circle, it's not the right word. I drew a square here because this is actually something that was very unexpected. And it turned out that there was a bit of a scar in the cortical surface on the left frontal lobe. And this had never been really described in any of the reports, even from the MRI studies that were done in the 90s and in the 2000s. So this was very intriguing. Now, our colleagues at MGH thought this would have might have been a scar that was made at autopsy. But when we looked back at the scan that was done of the brain in the skull, so this was the cadaveric scan. This was HM who was dead, but he was in the scanner. So the brain is still in the skull, as you can see. And we could easily localize this lesion, which you notice here on this panel, where I have my mouse, where there is this red dot, that this lesion actually created quite a diffuse pathology in the underlying white matter. So this was an old lesion. And I personally, the explanation that I gave for this unintentional lesion is probably due to the procedure and how for these lobectomies, the surgeon had to keep the frontal lobe lifted in order to see the medial temporal lobes and to access it with a scalpel and with a suction tube. So it's very likely, at least that was the occasion where this scarring was made. In fact, that's the only explanation I can give as an anatomist, because it's right on the path of the spatula that you can see here. I don't know what you think, Barry, if this is plausible, but that's the explanation I gave in the publication eventually. And whether this has affected his behavior, it's hard to say, because it is a shallow scar. It's about I would say it's the surface of a dime, maybe a little larger than a dime. And there is underlying white matter pathology, but I am not a neuropsychologist by training, so it's very hard to say whether that could have affected his behavior.
So now
And
it's encased.
yes, so what did we have to do here? So now, this was kind of it was nice to write that grant because, the sky was the limit. We're going to do this, we're going to do that. But in practice, the idea of slicing, the idea of creating a collection and an uninterrupted, complete collection of giant brain slices from a whole human brain had never been done. And Barry and I were talking a few days ago when we were sharing notes that, he's done this type of work. And what happens is that when you actually prepare this block and you freeze it for then, to be cut on a cryostat, very often this tissue tends to crack because, it's very, very cold temperature. We're talking about dry ice temperatures. So we were we did tests on other specimens, but eventually, that was the only way we could have done it, because embedding this whole brain in paraffin and to do it the old-fashioned way would have meant waiting for a long time and then shrinking the brain to half its size. When you do the normal pathological procedure in a tissue specimen, they really shrink half their size. So, we wanted to also maintain a good anatomical integrity. And we encased it in gelatin because the cerebral cortex is very convoluted, and when you cut in cross section, you can meet all these little pieces are not held together now by the geometry of the tissue, and they get lost. So this was a huge block. It was about 20 inches tall, and eventually we made a little nick on one side to know what was right and what was left. We learned this because once you freeze this block of gelatin, and here it shows where we froze it in this kind of Sputnik-looking freezing chamber. It took about 6 hours to get it down to the temperature that needed to be. But once you freeze it, then it becomes solid white. You can't see the brain inside anymore. And this is what we built to do it. So this was also part of the innovation, given that this is an innovation series. What was very innovating about this project was really the idea of recreating a digital virtual brain from a human at a microscopic resolution. And so we had to, yes, go ahead.
And you actually broadcast that on the internet, correct?
Yeah, I'm gonna show it. Yeah, and we did it because, like I said, we thought that it would have been a good idea to let everybody in, instead of doing it, in hiding and then publish a paper. I wanted to make a science education event out of it. It was a really good opportunity to really expose the public to a lesser known, at least at the time. This was before football concussion, CTE. So this was before pathology was hot. This was a very lesser known branch of neuroscience, this sort of slicing and dicing of brains. So we wanted to really show what the beauty in this type of anatomical work. And so this is at the very beginning. Like I said, we built these freezing cups to surround the brain so it would stay frozen for this long procedure. And I wanted to pay attention to this camera on top, because this is very important for making our 3D model. And so as we moved along, this is 53 hours later, and this is the last slice of HM. So you can see this was 53 uninterrupted. This was 4 days uninterrupted work at the lab with my staff. And so we were really, that's where I got my training for not sleeping, which is very useful now that I have a 5-month-old baby. And this is at the end of the procedure. So you see there is a camera directly on top that was always taking photos of the block. And this is the whole setup, which is really like a lot of hardware for a small, delicate brain. But this is what it took. So you see these are the chillers that pump frozen isopentane into these cups. There is a monitor to the left where one of the lab members would always check for each and every photograph that was taken as I was slicing. This is me and Sukorkin behind me. And so this is how it goes. I mean, this is how it went. Essentially, we started from the top, from the tip of the frontal lobes, and we slowly made our way to the end of the brain. And here I'm already, you see how much shorter now the block is, because this is the last night of cutting. And as we did this process, we were collecting the tissue slices. Uh, and we collected a lot of them, because all in all, we acquired 2,401 tissue slices. And the beauty about having the camera on top is that it allowed us then to really get a very good view of the brain as we were slicing. And then you see the lesion here on this side, and it just kind of came and left. But so this is essentially a movie made out of all the 2,401 photos that we took as I was slicing, right directly above the tissue block. And now we started seeing the lesion. You can see the two temporal lobes here at the bottom of the brain. And what was actually more intriguing and more exciting than the lesion was to see what appeared to be hippocampus. And we saw it as we were slicing. And those who have a trained eye, they will see it in this image. The chem is not supposed to have a hippocampus. So why are we seeing this layered structure? And after the procedure, we were able to, because we had this unabridged series of images through the entire brain, we were able to actually reconstruct the brain completely. So this is a three-dimensional monolithic reconstruction, several terabytes big, and it's essentially an MRI, but made on the physical brain. So it's hundreds of times more accurate in terms of resolution and contrast than an MRI would be. But just like an MRI, it allows us to go from anywhere in the brain and to really analyze many different views. I mean, we really wanted to reconstruct the geometry of the lesion because the borders of the lesion were extremely important, what areas they affected, what structures were destroyed, and most importantly, what structures were actually left. And as we see here, eventually we were able to, yes.
Yeah. Yeah, I think I had a question about the thickness of these slides. They were about 70 microns. I mean,
yes, 70 microns
microns.
is 70 thousandths of a millimeter.
Yeah,
and
yeah.
essentially, it's like a hair. Yeah. So essentially, this was, it was a very interesting result because, and again, if we hadn't really rebuilt the brain like that in 3D, it would have been very difficult to prove it. So, again, Scoville had planned to go within, to go into about 8 centimeters into the temporal lobe, but somehow he missed the mark. Now, as an anatomist, I can see why, because, as I'm sitting now this way, my hippocampus actually, both of them on each hemisphere, they actually bend upwards.
Yeah.
At some point. So if somebody were trying to destroy them, just going through my forehead and going straight, he would miss exactly half of them, which is the part that he missed. So there must have been some maybe overconfidence, maybe it was just the procedure. He could not really see well.
Well, knowing him and his flamboyant nature, I think that it was probably overconfidence. To be very frank with you,
maybe he did it very quickly.
He was bigger than life, bigger than life. But
right.
Dr. Annese, we don't have a lot of time, but I wanted to say, I mentioned that this closed a chapter for me, but you basically said when I mentioned that to you, this basically opens up a chapter, doesn't it?
Well, I mean, the whole point of this project, we went forward. We wanted to be absolutely sure. We mounted section on glass. We stained them. We used Google software to actually create a map that everybody, expert and non-experts, could use at home to explore this brain. So the idea of an open source brain was this, was, there is so much information to be gathered out of this brain, and there is so much information on HM as a patient, as an amnesic patient. We're gonna leave behind this data set that allows to answer every question that somebody can
Yeah,
pose in the future.
exactly.
So now all the data is available in this website that was also funded by a later grant by the National Science Foundation. But I think that in the last few minutes that we have, I remember that you told me you wanted to touch on the fact that we were broadcasting this procedure, correct?
Yeah, there were 400,000 people actually
Yeah, I
watching
mean
it, correct?
that was really the surprising fact that I have this video here, which is what people were seeing on their screens. Uh, this was 2009, so even streaming and doing these things online, it was not the level of sophistication that we have now.
No.
And
Yeah.
so we did what we go. We had a camera, and this is the actual speed. So to me, it was unbelievable that. That we had so many people actually watching this very boring procedure, and because we were doing it over 4 days, so we had I collected some of the tweets that you asked me to see. So what was happening while we were slicing, people, and this was also early on
Hmm.
in Twitter,
Yeah.
and I don't think it was so widespread as now as a
Hmm.
platform. But it was funny to see that every hour people would just be logging in and say, you have these funny ones that, oh my God, I gotta pick up the kids at school, but I don't wanna leave the brain. Or then there were the
Yeah.
very serious ones, like, are they saving the sections? Because I think that if you pick it up like that, you need to. Uh,
Hmm.
there were a lady that liked the black gloves. She was like,
Yeah.
"Oh, I love those black gloves, the latex gloves. They're very stylish." So we had all these different, and I think this was an experiment within the experiment, because it really demonstrated that a lot of science education programs, they really dilute or they simplify science a lot. And
Hmm.
what we did was simply to let everybody in our lab uh, and just be a witness of what we were doing. If it was boring, it's boring. Neuroscience can be very boring, uh, but it seems like there was something so I think it was like a novelty on the web
Well,
that it became kind of viral. Now they would say so. It was it
it's
was it really taught
it
me a
certainly
lot.
was. It certainly was viral, and it was actually historic for the field of neuroscience and medicine in general. The connection between Dr. Annese and myself is that when right after Dr. Scoville did this particular surgery, he opened up a lab called the Limbic Diencephalic Laboratory, Neuroscience Laboratory, and he had one lab assistant, an undergraduate, who he taught to do this procedure on monkeys, so he could actually test to see what actually happened with HM. And he tested it on many monkeys. And that lab assistant was me, actually, as an undergrad. So when I first heard that Dr. Annese was going to get HM's brain, it sort of closed a chapter in my own career because that's really what inspired me to become a neuroscientist and go into the field. So that's why I was saying initially that he and I have both a professional and a emotional connection to HM. I don't, fortunately, I don't do any more vivisection. I'm an anti-vivisectionist. But back in those days, that was the state of the art, and I had a very intimate connection with HM and the animal research that it inspired. The fact of the matter is that Scoville didn't take out all of the hippocampus, but what it did teach us is that memory really is made up of different components. And there's a short term memory and different types of short term memory. that eventually get settled into long-term memory if it's significant enough. And the fact that the amygdala is attached to the hippocampus, and the amygdala is the emotional part of the brain, is an indication that those memories that are most emotionally important to us are the ones that get turned into long-term memory. I think we've got to wrap it up, but I really appreciate you being here. And listen, I want you to know who's going to be speaking next time. It's going to be Greg Passmore. He's going to be speaking on the 27th. I've known Greg for about 20 years, during which I followed his travels to some of the most exotic places on Earth. What does a Czech Roman Catholic chapel made out of 70,000 human skeletons, the largest bat caves in the world, Jesus' resting place in the Church of the Holy Sepulchre in Jerusalem, and ice caves in Austria? What do they have in common? They're some of the most fascinating places in the world that are also inaccessible, dangerous, or too fragile to visit or study. Protection for these special locations is limited because they're hidden from governing bodies, conservators, and the public. Today, protection of these incredible venues relies on secrecy. Our understanding of them is based on fragmentary data and anecdotal interpretation. Now, Greg has not only visited them, but he's also captured them visually with sensing and imaging devices that he's invented himself, producing volumetric models of these fascinating places that you can travel through as if you're in virtual reality. You're going to leave this presentation on the 27th having explored some of these rarefied sites and discover what Greg has learned from his explorations. I've seen all of these, and they are absolutely mind-boggling as you're traveling through them, and at a resolution of less than a millimeter. Fascinating stuff, incredible technology that is leading edge, and it's going to be well, basically, it's going to preserve history. There was a cave in Guatemala with some beautiful paintings that were destroyed recently with graffiti. That's that's horrible, and that should never happen. And one of the things that Greg is doing is he's preserving all of these magnificent sites. And I'm looking forward to his presentation because he never fails to amaze his audiences, and he's given these lectures all over the world. So I want to thank everyone for joining us, and I want to thank Dr. Annese again. Thank you so
And
much for joining us.
thank you, Barry. Am
And
I invited to the next talk? I want to
yes,
see.
absolutely,
Okay.
absolutely. You get a
There's a lot
VIP
in
seat.
common. Perfect.
Yes.
Thank you.
Thank you very much.
Thank you
Good
again.
night.
Bye.
Good night.